Today we're going to start our next section of the course talking about AC circuits. So for AC circuits, it's just like DC circuits, except everything's changing all the time. So we want to talk about time dependence of a bunch of quantities, right? So instead of voltage, which has generally been a constant, we're going to go to some oscillating voltage that is a function of time, right? And the same for our current. This is also, now becoming a function of time. Convention for these variables actually shows that for the time dependent ones, we use lowercase variables, and we're going to use the capital versions to represent the amplitudes of these once we actually take this oscillation into account. Our components are going to be the same. We're still using resistors. We're going to start using capacitors and inductors, which we haven't seen in this class, but hopefully you've seen in other classes. And we are going to use AC voltage sources that generally is drawn like this with a little sine wave in there to show you that it's producing a sinusoidal voltage. Sometimes these are marked with the polarity, sometimes they're not. Often it doesn't matter, but when it does, it's assumed that the top part is positive. So the way we're going to analyze AC circuits is we're only going to deal with one frequency at a time. And the reason for this is, as you will see eventually, because everything we're doing is linear, if you want to know what's happening in a system with more than one frequencies, you just analyze what's going on for the individual frequencies and then add those results together to get your total result. So it's actually pretty nice, and that's part of what makes this analysis very easy, the linearity. So one frequency at a time, and let's get started. So let's say I have a resistor. So we're gonna look at our three components individually to start with. So let's say I have a resistor that is connected to a AC voltage source. So I have something that looks like this and like that. Now, my voltage source is making a voltage V of t that is oscillating with time. And we'll say this voltage is some amplitude, capital V, or we could use capital V naught, just to show that it's some constant amplitude, capital V, times the sine of omega t plus phi. So we're keeping this oscillation totally general. At time t equals 0, we can be anywhere in the oscillation as determined by this phase phi. And omega here is our angular frequency, which is going to be more convenient to use than our regular frequency, but omega is equal to 2 pi f. I expect everybody has already seen that, but if you haven't, here it is. And the units of omega are radians per second. Lots of arrows. Okay, so if this is our voltage that's being applied to our resistor, we can figure out what the current is flowing in our resistor at any moment in time, and that is because Ohm's law has to be true at any instant. It's not just true averaged over long periods. At any instant in time, V equals IR. So that I value at time t has to be equal to that V value at time t over R. So this is just V naught over R sine of omega t plus phi. This, of course, is going to give us some current magnitude. I guess we could call that I naught or something like this for this oscillation. This is for a resistor. The voltage oscillates like this, the current oscillates like this, and if we were to draw a graph of the voltage and current on the same axes, we would see, I'm drawing both voltage and current here. Their peaks are going to be in the same place, their zeros are going to be in the same place, and their opposite direction extremum is going to be in the same place also. All right. For a capacitor, we have different governing equations. So for a capacitor, the important equation is Q equals CV. So this is kind of like kind of like Ohm's law for a capacitor, I guess, except our we don't have current, we have the total charge that's accumulated on the capacitor. So if our charge is a function of time, our capacitance is constant. That means our voltage is also a function of time, or vice versa. If our voltage is a function of time, our charge must also be a function of time. So we can write this as if this voltage is still, I'll write that up here. V of t is equal to V naught sine of omega t plus phi, right? So we can plug that in here. So Q of t equals C V naught sine of omega t plus phi. Okay. So this is an equation for the charge. So the amount of charge on the capacitor, sometimes it's positive, sometimes it's negative, and sometimes it's zero, it's oscillating up and down. And the current that is flowing on and off that capacitor, lowercase I, the current that is flowing on and off that capacitor is of course a function of time also, and it is the derivative of the charge. So if the charge on the capacitor plates is increasing, that is a positive current flowing into the capacitor, and vice versa. If dq dt equals 0, no charge is moving, well then the current is just 0. So anyway, I of t equals d q dt, and we have an expression for what q of t is here, right? So we can take the derivative of sine of omega t plus phi, and we get cosine of omega t plus phi. Oh, times an extra factor of omega. That's important. So we have c, v naught, these are constants. Cosine omega t plus phi times omega. The omega comes from the chain rule, since the omega is multiplying our t inside the cosine. All right, so if we are to look at the relationship between the voltage and the current, now we see that they are not going to line up so nicely, right? We'll draw these graphs more later, but if our voltage looks like this, our voltage is like sine, our current is like cosine. So this is our current here. Yeah, more on that later, but the point is these are not lined up anymore. The current and the voltage are out of phase. Okay, we can, kind of inspired by Ohm's law, we could write an equation that is a ratio of our maximum voltage to our maximum current. Remember now, C V naught omega times the cosine of stuff. This is like the amplitude of our current, right? I of t is some stuff times cosine, and that stuff, that is the amplitude of our I oscillation. So this is I0. So remember, for Ohm's law, we have R is equal to V over I. For this, let's look at the ratio of V over I for the capacitor. So that is we're looking at the amplitude, so that's V naught over I naught. So that is equal to V naught over C V naught omega. So the V naughts cancel, and we get 1 over omega C. So the ratio of the current to the voltage is kind of like, there is this ratio kind of like Ohm's law, but it's not a resistance that we get. It is 1 over omega C that we get, and we will be seeing that later on, so hold on to that. So 90 degrees out of phase, the ratio between the amplitudes is 1 over omega C. All right, inductor. So let's say we have an inductor hooked up to our voltage source. For an inductor, the equation that has to be true at every point in time is our voltage is equal to L, the inductance, times di dt. So this is kind of the opposite of a capacitor, where the capacitor, the current was proportional to the derivative of the voltage, which ended up being the derivative of the charge, right? So if we flip this around and solve for I, this is, I'm playing fast and loose with my math here, but you'll see what's going on. So we get di dt is equal to 1 over L times v of t, which means I is the integral of the stuff on the right. So that's 1 over L integral of v of t dt. Okay, we're not going to be super careful about our bounds, and yes, this could be different by a constant, but we're going to ignore that. We're just looking at kind of the form of the solution. And the antiderivative of this is going to be v naught times minus cosine of omega t plus phi times a factor of 1 over omega that we get from the chain rule. So this is minus cosine of omega t plus phi times 1 over omega. Okay, so rearranging this, we get 1 over omega L times this minus cosine stuff. So again, if we're looking for the ratio of the maximum voltage to the maximum current, this part right here is our maximum current I naught, right? So V naught over this is going to be, oh, sorry, I missed something. There should be a V naught in here also, because that's part of this oscillating function. So this should be a V naught. There we go. This is V naught over omega L. And so then V naught over I naught, these are the amplitudes, is equal to V naught over omega L, which is equal to omega L. So we have a similar relationship between the amplitudes of the current and voltage for the inductor, and it is equal to omega L. So we have omega L, 1 over omega C, and resistance. These all three of these things are like ratios of the amplitudes of these oscillations. Oh, and since this is a minus cosine and this is still a sine, our current and voltage are still out of phase, and we'll talk more about that later. To finish this video, I'd like to talk a little bit more about this voltage to current ratio that we were just talking about. So our resistance is what we have in resistors, right? And that, for these oscillating circuits, we have V naught over I naught is equal to R. And V and I are in phase. So the analogous value for capacitance and inductance that we just saw also has a name. It is called reactance, kind of because it doesn't resist the flow of current, it reacts to the flow of current. This is still equal to V naught over I naught, but this is for capacitors and inductors. So resistance is for resistors, reactance is for capacitors and inductors. And so this ratio, V over I, this is called X, capital X. So this X value can be used for inductors or capacitors, and it's written with a subscript usually. So the inductor reactance, as we just saw, is equal to omega L, and the inductor capacitance, my L's and my C's sometimes look the same, so hopefully that works, is 1 over omega C. So these are our reactances for those two things. And they kind of behave like resistance in that, the smaller the reactances, the bigger the current we get for a particular voltage. And a small reactance could be a low frequency or a small value of the inductor, or a big value of the capacitor. So if the reactance is very low, we get, like I said, we get a big current for a particular amount of voltage. So for both of these, I and V are out of phase. meaning that these sign functions are shifted relative to each other. And again, we'll talk more about that in a little bit. So we can really only use these for single components. And what we're going to talk about next in the next video is how do we deal with combinations of these things. So if we have multiple inductors, well, multiple inductors or multiple capacitors is not so hard. What if we have a mixture of resistors and inductors or resistors and capacitors or something like that? How does that affect the behavior of our AC circuits? So that's what we're going to talk about next.